Recording. Okay, so today is Legion Week. So what I want to talk about today is to effectively go over effectively how instance creation works, and how we create instances and manage memory stuff inside of Legion. So the entry point for all instance creation and all memory allocation, from the application's perspective, comes to the mapper. Right, mappers create physical instances for logical regions and use those for mapping their tasks. And so, to do that, there's a mapper call, and hopefully you guys all remember from last week, we're looking at the mapper manager, or I guess 2 weeks ago, we're looking at the mapper manager here, and this is the find or create physical instance call. There are a whole bunch of calls to either create instances directly or do these find or create, right? You can just make a normal create physical instance, just tell the runtime to make an instance or try to make one. It does return a Boolean saying whether that succeeds or not. But there's also this find or create call, which effectively does an atomic check to see, are there any instances in this memory that will already satisfy, the constraints, in particular, like the layout constraints, which we're going to look at today, and the sets of logical regions that I need for this instance. And if so, you can just return that to me. But if you can't find one, then try to create one. Right, and the reason that needs to be atomic is two different mappers might try to create the same instance in the same memory, right? And they might want to deduplicate those so that they only see one, right? And so this find or create operation is going to be an atomic thing, and we'll see how that is implemented today. There are other parameters here that we'll look at today, do you want these region bounds to be tight, right? What are the priorities? Do you need to acquire this instance? We'll see a little bit of those. There's also some other return values here, do you want to know the footprint of the instance size that you are asking for? Or, if you were unable to find an instance, or make one, what layout constraint caused that not to be successful, right? So anyway, we're going to dive in here to this find or create physical instance call. And you notice, from last time, we're pausing the mapper call around this because this is going to be a potentially long latency operation. So we pause the mapper in the process of doing this. Okay, so if you call runtime, we're going to jump into the main runtime object inside of Legion, which is actually going to be, the runtime singleton that actually performs, that manages all the state for the Legion runtime. So we're going to dispatch onto that, just tell it to go try to find or create a physical instance in this particular target memory. So if we do that, let's see, and jump over to the next tab here, right? So actually, we want the runtime one, right? So here's the corresponding call in the runtime. We've dispatched into the main runtime object in Legion, and we're asking it to do the same thing. So the first thing that Legion is going to do is it's going to try to find this object, which we call the memory manager for this particular target memory, right? And the idea of a memory manager is that this is going to be the thing that maintains. It's going to be an object inside of Legion. It's going to maintain the state of every single memory that this node is sort of tracking. So if I go over here to runtime.h and I look for memory manager, here's our memory manager class. There's a whole bunch of stuff in here. I think the interesting thing that this mainly does is manage the lifetime of instances and tracking instances that are allocated in this memory. There's a bunch of methods and stuff. We'll go through some of these today, but not all of them. If you look at some of the member variables, right, this is the name of the realm memory that we're tracking. This is the node that actually owns that memory, right? We might have a copy of this memory manager on a remote node. We'll talk about that today. We know how much capacity, how much, a rough estimate of how much remaining capacity we have based on the instances that have been allocated in this instance or in this memory. There's some stuff for eager allocations, which we're not going to look at because hopefully that will actually disappear in the near future. But importantly, there's going to be some important data structures here that actually track, all the instances that are allocated in this memory. So there's going to be effectively a map here that tracks, in a particular region tree, what are all the instances stored in that. You can see this tree instances is typed F right here. It's a map of these physical manager objects, which are going to represent an instance along with their garbage collection priorities and stuff. So we'll look at some of that. These collectible instances are all the instances that are eligible for collection because they don't have valid data. So we'll take a look at this data structure a little bit today, and how we actually do garbage collection when we can't allocate an instance right away. And we're also going to look at this class that exists inside of the memory manager, which is the garbage collector class, which helps us to do collections whenever we need to clean up some memory to try and make space for creating new instances. So we'll dive into that a little bit. Okay, so the first thing that we do is we find this memory manager object. Let's take a brief detour to look at what that does. It's really simple. So the runtime maintains a list of all the memory managers, which, on this node effectively tracks, a mapping from the memories over to the memory managers, right? There's a little read-only lock here. Most of the time we find it, we return it, right? If it's the first time we've seen this memory referenced, right, what we'll do is we'll actually create a new memory manager to track this. It might be one on a remote node. We'll see a little bit about, how that works later. But effectively, you retake the lock, check again, make sure it's not still not there. If not, make it, put it in the store in the data structure and return it. And so that'll actually create your memory manager object on your local node to track this particular memory that's being referenced. So we can go back to find or create physical instance here. Right, and so once you've got your memory manager, you're just going to dispatch to the same, find or create physical instance here with all the same arguments, except your target memory has gone away now because you're dispatching directly to the memory manager that's actually going to manage this memory. So if we keep searching for this, we actually end up on the memory manager version of this method. And you'll see that the first thing that we actually check here, right, is whether we are on the owner node for this particular memory. So every realm memory that exists, Legion designates one particular node to be the one that's going to be the quote unquote owner of this. And we do this today using the if I actually look at the memory manager constructor, you can actually see how is owner is determined, right? Effectively, it's checking is the address space associated with this memory the same one that I'm in on this local Legion runtime instance, right? And if that's the case, then we end up being the owner, right? And otherwise we're going to designate ourselves not the owner, and we're just going to be sort of tracking the names of instances that exist in that memory, but we don't actually know, that we won't actually have privileges to do allocations and deletions if we're not the owner. And I'll talk a little bit about why the owner node is the only one does allocations in just a minute. Okay. So coming back to find or create instance, the first thing we do is we check to see if we are the owner, right? If we're not the owner, well, we don't necessarily need to send a message to the mapper right away. So effectively, sorry about that. One too many fingers on the touchpad. Okay, so if we're not the owner, right, it doesn't mean that we have to send a message to the owner right away to try to do this operation. What we can do is, if there are any instances that we know about on this local node, we can actually go test those to see if we can find one that is actually something that we can actually return right away without actually having to go talk to the manager or to the owner node, the memory manager on the owner node. So I'm actually not going to look at this because we're going to look at a variation of this method a little bit later today. You guys can go take a look at this find valid instance. It's going to do something very, very similar to find satisfying instance down here. So I'm actually not going to dive into what find valid instance does today. But effectively, we can test locally, are there any instances that we know that satisfy these layout constraints and stuff that we need right now? If so, we can just return that. We're done. We don't even have to talk to the owner. But if we can't do that, we don't find anything that actually satisfies, right? Then what we do is we turn around and we actually will send a message off to the owner node to actually go do this primitive operation. So what I'm not going to do is effectively what we do is we serialize up all this data. I'm not going to show you how messages work today. That's still on our future to-do list. But effectively we make a user event, we package up some data, we send off a message, we wait for the message to come back to us, right, and populate all of our data, and then we can return the result of this. And so that's the case that we're not the owner node. Now, once this message arrives on the owner node, what it will do is it will actually call back into this method. You're not going to come back into memory manager, find or create physical instance, but this time we'll be on the owner node. And so we'll do the exact same thing. So the same code sort of comes back around to us on the owner node when we're actually ready to actually do this call whenever you send one of these messages. This is a very common pattern in Legion realm where you have multiple copies of an object that actually has a concept of an owner and a non-owner, right? And you do checks to see can I do anything on the non-owner node? And if so, then I'm done. If not, then I send a message to the owner and it comes back around to the same function on the owner node object. So That's all that's happening here. So we package up all of the arguments, we serialize them all up into a buffer, we send off a message, right? And then the results will come back to us and fill it back in. So I'm not going to show you how this works. It's a lot of boring bit packing and unpacking and stuff like that. But effectively, it's just dispatching off to the owner node and sending the results back when it's done. Okay. So when we are actually on the owner node, right, what we need to do is we need to do a test to see if we can actually find a satisfying instance first, right? Can we find an instance that already exists that matches all the constraints that we want? If so, then we need to return that, and if not, then we need to go try to make an instance, right? So we're gonna create one of these instance builder objects to help us in case we do need to build something. We're gonna do that before we acquire this allocation privilege. So you remember that I told you that the check to see whether you find and/or create has to be atomic. Right, so this acquire allocation privilege, what it's doing is effectively checking to see, are we the only ones potentially trying to do one of these atomic find or create operations, right? If so, right, we may need to wait here to make sure that, we're operating atomically with anybody else who's trying to do a find or create physical instance, right? And so this acquire allocation privilege, if we go take a quick detour into that, right, we're just making a little user event to say when we're done. Right, we're adding that to a list of pending allocation attempts if we're the first one, or we pop the first one, or sorry, we pop the one off the back if we're not the first one to get the one that we need to wait on to finish before us, right? And then we stick our thing on the back that will trigger when we're done actually running. And then what you're going to see is there's also a release allocation privilege that will actually trigger our event and wake up anybody and pop ourselves off the list when we're done. To notify anyone else who's waiting for us to finish our atomic operation on this find or create to do something similar. Let's go back to find or create physical instance. That's the runtime version. Here's the memory manager one. Okay, so effectively this is giving us that atomic property that I called out, and here's the release call, by the way, when we're done. Right, so they're matching acquires and releases for these allocation privileges to make sure that this operation is atomic with respect to any others that are being done. Okay, so the first thing we want to do is we want to check to see whether or not we can find an instance that already matches the existing constraints that the user has passed in. Right, we don't want to actually do the allocation unless it's absolutely necessary. So let's go take a look at find satisfying instance here. Okay, so here's the memory manager call to find satisfying instance. We're passing in a set of layout constraints. And by the way, we will look at these layout constraints. I promise you we'll expand the structure to show you a little bit what that is. But that's actually a user-facing API, so it's not too unfamiliar to most of you, I hope. Also, a set of regions that need to be satisfied, right? And then we're returning our name of our physical instance that's going to be the result, right? And there's also calls in here to tell us whether we need to acquire, whether the region bounds need to be tight, whether we're doing a remote call, and so forth. So the first thing that we do in this case, right, is we're checking to see if there needs to be, if the user has asked us for a specific logical set of logical regions, we need to know which region tree they're in. So we can grab a preemptive set of instances to actually go and test to see if they satisfy all of these constraints. Right, so we look for the name of the region tree ID. There are some people who actually pass this in with no region tree ID. They're just looking for all the instances that satisfy a particular constraint. That's a very special case. In general, you're going to have a region tree ID where there's some logical regions in here that actually you need to satisfy. And if so, that allows us to easily filter out instances that we can ignore, right? Because we only care about instances in this memory that are associated with a particular region tree ID, right? Only ones that are aligned with our particular logical regions are going to be ones that satisfy. We can already prune out all the instances that are not associated with our particular region tree ID, right? So we go through here. We're taking a lock here in this data structure in read-only mode because we're just reading through it to get a list of candidate instances to consider. We're going to do more expensive tests on their layout constraints and stuff here in a minute. But we're going to hold a lock here for this first part. So we do just a very basic filter, testing to see, can we find any instances in the same region tree ID, right? This is the weird case where they don't have any regions that they're caring about. And like I said, those are some unusual use cases, so you can mostly ignore those. right? And so in the case where we have some candidates, right, and we know that our region tree ID is 0, this is the common case. Right now we get to do some more expensive layout constraint tests. So far we've only tested that, like, these instances were made for the same region tree as the regions that we're looking for. Right, and so the next thing we need to do is test whether these instances actually have any space or have enough space for all the logical regions that were passed into this query. So what we do is we build one of these index-based expressions, which I haven't told you about yet, but just think about these as like sort of a representation of the union of all of the index spaces for those regions that you can actually see the union call here if there are more than one of them. And effectively, that's just getting sort of what are the bounds of this. What kind of space does this instance need to have in order to support all those logical regions, and can we meet that? So the first thing we do, we iterate over our candidates now. Right, and what we do is we check to see whether all the space is actually met. You can see here's where we pass in the tight region bounds, which effectively says, does this need to match exactly, or can I over approximate? Right, so is it possible that the instance is over approximating the set of logical regions? In many cases that's okay, but some users actually say no, that's not okay. You actually need to precisely match the set of instances. Or the set of regions that I'm asking for, so that I'm not wasting any space, right? And so users can control that with this tight region bounds. And this meets expression, which I'm not going to show you here, but effectively what it does is it tests the space for the logical regions, against the space that the instance actually has, and says, whether or not it satisfies, the space requirements and whether it's precise or not. And so if that doesn't pass, then we can skip this. And then the next step is to do the even more expensive constraint check, which is to check, all these layout constraint set things that were passed in by the user against these particular instances, or against this particular instance, and test to see if if they're all satisfied. And so let's actually take a look, and you'll see that I'm using this entails call. I'm going to explain what this is. So let's actually go take a look at what a layout constraint set is. And we'll do a quick detour, and we'll look at what this entails method does and how it works, and some of the other things that exist on it. So let's see. So here's legion constraint.h. This is actually a public user-facing API. So if I look for a layout constraint set, if I can type, a layout constraint set is just a set of constraints. There's all sorts of constraints in here. So we've got specialized constraints, field constraints, memories, pointers, paddings, ordering, tiling, dimension, alignment, offsets, all sorts of constraints that can exist on a particular instance layout that you might want to describe. And so I'm not going to go through every single one of these kinds of constraints here. These are actually public, and they all exist in this file. So like, for example, if I look at a memory constraint here, right, a memory constraint is saying, what kind of memory do you expect this instance to actually live in? So it has a memory kind, and whether it's been set or not. You can also have like field constraints that show, what set of fields do you expect to have in this instance? Do they need to be contiguous? Do they have to be laid out in the specific order of this field set, right? So there's all sorts of constraints on fields, right? And I'll let you guys go take a look at all the other kinds of constraints that exist in a layout constraint set. But users use this to specify effectively what layouts they expect to see on these instances, right? Now, these layout constraint sets actually have two very important methods on them for testing constraints against each other. So there's the entails method here, which is testing for entailment, and then there's a conflicts method, which actually tests for conflicts between this layout constraint and another layout constraint. And you'll see each of the sub constraints have similar methods. They all have entails and conflicts test, which we'll be using in different places. So in order to sort of show you what the concept of entailment and conflict actually mean, I prepared a little example here. So effectively, constraints are partial, right? So like they actually define like a partial order on them, right? So like a constraint set doesn't have to be fully specified, right? It doesn't. You may have only some of the constraints filled in the layout constraint set relative to something else, right? And so that it effectively creates like a type hierarchy. And type hierarchies are all something that we're familiar with type systems and stuff like that. So I've given you like a really simple type hierarchy here. We've got like a base type of animal, and we've got two specified types of dog and cat, right? And so conflicts is effectively testing whether or not, one type can be another type, right? So conflicts dog and animal. Well, that's false because like a dog may be an animal, right? And so forth, right? But conflicts dog and cat. That's definitely true, right? A dog can never be a cat. And these arguments on conflicts are commutative, right? We can swap them around, right? And the same relationships will hold. Now, entails is a different thing, right? Entails is effectively testing for partial, satisfying cases, right? So like, is a dog a kind of an animal, right? That's true, right? A cat is also a kind of an animal, right? So a cat entails that it is an animal, right? But entails dog and cat is false. And importantly, these arguments, to this relationship are not commutative, right? So like an animal does not necessarily have to be a dog, right? And similarly, being an animal does not mean that you're a cat either, right? So that's also false, right? And so just keep those sort of rules in mind. I use this as like a good intuition for like when you look at entailment and conflicts. We use them in different ways inside of Legion, but you'll see that all of our constraints, have these relationships with each other, so you can test them. You can test like layout constraint sets against other layout constraint sets. You can even test like individual constraints against each other. And that's how actually like the layout constraint set is actually evaluated and so forth. So anyway, when you're thinking about entailment and conflicts, these are the things to actually sort of go like just keep this sort of analogy in your head when you're thinking about what they're doing. So if I jump back to the code here, right? So every one of these things in this layout constraint set, support this method. And we can test, for entailment and conflicts on all of the subconstraints and so forth. Also point out there's like methods for, serializing and deserializing these constraints. They get packed up pretty easily. And often, like in the case where we're actually moving the layout constraints, from one node to another, like we saw earlier in the case where we like did this call on a remote node, right? That's how we pack up these constraints and ship them over to another node. Okay, let's try and jump back to here where we've got our entails call. Right, so now you can actually see how this entails method is actually working, right? It's effectively saying, do these physical instances that already exist entail the constraints that the user has passed in, right? And we're using entails here because constraints can be underspecified, right? A user may not have fully specified the constraints for their layout. They may say, I care about some of these constraints a lot, but the other ones I don't really care so much about. So I've only given you like a partial specification of the constraints that I need for this particular physical manager or instance that I'm trying to make, right? And so in that case, it's sufficient for our instance to actually just entail the constraints that that the user has actually asked for. And if they do, then we've actually gone and found an instance that actually satisfies all the things that the constraints the user passed in, and we're actually done. Right, so that's effectively, if you can jump into here, we're actually going to record this instance as the result, and then we can break out and we'll actually be done with this process. But if not, we keep going around the loop and keep testing more and more stuff to see if it succeeds. And if not, this found will never get set to true, and we'll end up exiting out of this method without actually having found any instances. Right. I'll add one little detail here. So the user can ask us to actually acquire this instance. One thing that we're going to do today is actually look at the garbage collection code to see how it actually works. But importantly, like these tests, right, for finding these instances can actually race with the garbage collector, right? So it's possible that these instances actually like, somebody else could actually be trying to just do a normal create, which might actually be running the garbage collection, right? And so we need to test that we're actually able to get a reference to this instance, do an acquire operation, right, before the garbage collector actually goes and eats this instance. Now, we don't have to do this. The user can tell us, like, no, I'll do the acquire later, right? You don't need to do it in the find or create call, right? But we give the option for performance reasons for users to actually ask us to actually do this acquire as part of the find or create, such that if they get a result, then they know they've already acquired it, and they don't need to worry about doing acquire later because they've already had it done for them. Right, so we're actually not going to dig into this method today. It requires some more knowledge about some internals of Legion that we haven't covered yet to actually test like this acquire and look at how the reference counting actually happens. But know that this acquire is effectively the primitive that is what's going to prevent this instance from being garbage collected throughout the rest of the mapper call until like the mapper either explicitly releases it or they return it as a result to us and the mapper call finishes, and then we release the acquire for them when it's safe to do so. So anyway, that's how we do the find call, right? We effectively iterated through all the instances that were potential candidates in this memory, and we've checked them all to see if they satisfied all our constraints, and if they did, then we're done, right? But if this method returns false, right, if we're not actually able to successfully find a satisfying instance, well, then we're going to actually have to go off and make a new instance. So let's jump back to find or create physical instance and look what happens after if we don't satisfy. Okay, there's runtime versions. Here's the memory manager version of it. Right, so if we found a satisfying instance and we return success, well, then we're done, right? We skip this if branch. We might need to save some of the outputs, like the size of the footprint of the instance that we made and so forth. And we can return that like we successfully found an instance and we're immediately done, right? But if we weren't able to find a satisfying instance that matched all of the constraints, well, now we need to actually go try to actually make one of those instances, right? So to do that, we're going to call into this allocate physical instance call, which is going to do what it's going to say. It's going to try to make a physical instance that actually, can represent, all these constraints and actually allocate the memory for it. And if it does succeed, it'll return a memory manager, which is, I pointed it a little bit. A memory manager is just a wrapper around a physical instance. It's going to manage the lifetime of that instance and store metadata associated with it. We're not going to look at these physical managers too much today, but if you see one, just know that this is like, managing a physical instance in memory somewhere, right? And storing all the metadata associated with it. So if we get a non-null, one of those that comes back to us, then, that means that we were successful in our allocation. We can save it. We can log some stuff for Legion Spy, record that we created this instance in our memory manager, and then, set created equals true to tell the user that, we actually made this physical instance. And then we go through the same path of returning success and so forth. And of course, if this is null, that means that we failed in our attempt to allocate this physical instance, and we weren't able to do all those things. So all the other defaults apply, and we can return back to the mapper to give it the result back. So let's actually dive in here to this allocate physical instance call. Okay, so here's allocate physical instance. It's actually, it looks conceptually simple, but there's going to be a lot of moving parts here for us to actually consider and actually understand what's actually happening. So the first thing we're going to try to do, like just, before we do anything, the first thing we do is we just try to make the instance, right? If it succeeds, well, then we're immediately done, right? So if we try to make the instance by asking this instance builder, we'll go take a look at this create physical instance call because we're going to invoke it a few times here. But effectively, if it succeeds, we get back a manager, fill in our results, and we're done, right? We can return right away. If that's not the case, well, then we're going to have to try to delete physical instances in this memory to try to make space. So we're going to make an instance of this garbage collector, and then we're going to loop around this garbage collector, keep trying to do collections. Like as long as the garbage collector doesn't think there's more stuff that it can collect, we'll keep trying to perform collections until the collection is actually done. Right, and then at the end of each collection where we think we've collected enough to make a new instance, we'll call create physical instance to see if that works. If it works, great, we're done. If not, we go around and keep trying to collect stuff until it's safe until we think that we're actually out of stuff to collect for this particular memory, and then we're effectively done at that point because we tried to collect everything we can, and we weren't able to make the instance. So the logic for this code is pretty simple, but a lot of these things are pretty deep, so we're actually going to take a look at some of these a little bit more. So this builder, the idea of the builder is effectively to give you like a little functor object that you can call over and over again to try to make this physical instance. So it's effectively saving some of the state needed to make a physical instance. Let's actually go try to take a look at this instance builder and create physical instance class. So yeah, here's my legion instances.h. And this is Legion instance.h, and this is our instance builder class. So effectively, when you make this, you pass in, the sets of regions you want to make this instance for, the layout constraints that you're making it for, some other details of stuff. They're two different constructors, but they mostly do this very similar kinds of things. And the idea is that we sort of save all the state needed to actually make this, to try to make this physical instance in here. And importantly, like, the real thing that happens is this initialize call just happens the first time that we try to create a physical instance. And if this method gets invoked many times, because say we went around that garbage collection loop a few times, right, this create physical instance call will actually be pretty efficient because we've initialized and saved a lot of the intermediate state that we need to actually try and make an instance. So let's actually look at the create physical instance call here. We'll actually take a little look into that, and then we'll go look at the garbage collector to see in the case where we actually don't succeed in making the instance, we have to try to collect stuff, right? So here's our instance builder class, right? And as I said, there's a little check here to see, like, are we the first time trying to make this instance? If so, call this initialize method. Initialize, I believe, is right down here. It does stuff like computing the space and domains and stuff for this instance. I'm not going to look at too many of these in detail. There's a lot of bookkeeping for storing stuff for actually making this physical instance. But effectively, it just initializes some of the state for making the different things inside this instance builder, and then it saves it in case like you actually need to compute these things over. If you actually get this create physical instance call several times, then you've already pre-computed all this stuff and saved it so that you don't need to redo it every time you get a call into create physical instance for this particular set of constraints and stuff like that. Okay, so you do that the first time through, and then after that, further calls into this method, like on this particular object, will not have to recompute stuff. Okay. So the first thing we're going to do here is, or the big thing that we really need to do is we need to make one of these realm layout objects that actually represent effectively the way to describe the instance layout for this instance in memory to realm. Because we're eventually going to have to ask realm to do the allocation. Realm is what actually manages memory and particular memories, right? And so we need to tell it sort of the layout of the instance that realm is going to create. And Legion has this nice constraint system for actually describing, layout constraints and stuff like that. Realm does not have that. Realm has a much more primitive way of describing instance layouts. And so we need to make is one of these, here's the actual type for it. It's a Realm instance layout generic, which is a very, it's sort of a base class for a templated, virtualized layout description that Realm actually really wants. So the first time through, we actually will make this, and then each remaining time we clone it because Realm effectively takes ownership every time you do an allocation call in. We'll take a look at this create layout method here in just 1 second to actually show you a little bit of how that works to make this Realm layout description. But once we've got that, we can actually look up the number of bytes that are required for this particular layout description. We can save that if we have to on the footprint. When you issue an allocation to Realm, you have to give it a profiling request to tell it, effectively the result, right? If you want to know if the allocation succeeds or not, you need to actually get Realm to effectively, give you back a profiling response to tell you whether or not the instance allocation succeeded, right? So when you do this, the call to actually do the allocation, right, that has to have a response. We can also add some of our own profiling. A lot of this here is like adding profiling for Legion Prof or Legion Spy, most of which is not especially interesting. But the main instance allocation call, let's see, make sure I find it here, is right here, create physical instance. Right, and so you do this and you get back an event saying, when this instance is actually ready, and you'll get a profiling response that sends a response back telling you whether or not the allocation actually succeeded. And you can see this is us waiting here for this profiling response to tell us whether this instance allocation succeeded, right? And Realm does this. I think it's a little annoying, but Realm does this because you might go off and do something while this allocation is pending and stuff like that. But for Legion, we actually need to know right away whether or not the instance allocation succeeds or not. So we wait for the profiling response, and when it does come back, we've actually already stored it in this instance builder object. I'm not going to show you that path today, but effectively what it does is it sets whether or not the allocation succeeded, and whether if the instance is still valid at this point, right, then we succeeded in our allocation. So I'm not showing you how this profiling response comes back. That'll be something for another day, but it comes back and it sets whether the instance is still valid or not. And so if it does succeed, right, then we can come down here and we actually populate more of the constraints if they weren't already populated. We fill them in, to describe precisely how this instance is actually made. If the user didn't actually pre-populate all these constraints, we fill in the remaining details to make this a complete set of layout constraints. And then we fill in some data structures and we actually make these physical managers to actually return back as part of the result in the case that we succeeded. In the case that we failed, right, we return null and give back a null memory manager, and that ends up going back around the loop, which we're going to go look at in the garbage collection here in just a little bit. But yeah, so effectively the main thing is to try to make these physical memory managers after you've succeeded in this allocation, and that effectively gives you a successful allocation back to the caller to say this allocation actually ended up succeeding. One thing I do want to point out here is that this event here that actually comes back right in Realm, you can actually get deferred allocations, which will be the topic of a Realm memory management talk in the future, where effectively, Realm might be able to say, I can promise you that this instance will be ready at some future point in time, right? But the instance, is not ready right now. Realm has seen enough deallocations to say, like, some memory has been deleted with or some instances have been previously deleted with event preconditions, meaning that they will be freed at some future point in time. But really, and so therefore I can do an allocation knowing that those instances will be ready in the future, right? Or this instance will be able to use the space from those deleted instances in the future and give you back a response. Right, and so that's what this ready event is actually signifying, is like, when that time in the future where the instance is actually going to be ready, right? And so that's different than the getting the response back from the profiler saying that the instance the instance allocation succeeded or not. So just make sure you keep those two things in your head straight. And I actually use an application event here to indicate that, right? To say that like this is dependent upon like deletions of instances from the rest of the application. Whereas this profiling event is actually a runtime event to track that, like, we got the response saying whether the instance allocation succeeded or not. So anyway, keep that in mind. I'll also say, like, if you see this Legion malloc instances, we're in the not def case. This is the common case. The Legion malloc instances case is one where we actually bypass Realm for doing these allocations, and we actually do all of our allocations with like malloc and free and CUDA malloc and CUDA free. And then tell Realm to attach to those with physical instances. The reason to do that is that like some tools like the CUDA memcheck debugger and stuff like that actually work better if you've actually like done every single allocation with like CUDA malloc and stuff. And so like this Legion malloc instances case is really an extreme case that is not used in practice in most cases, but can be helpful for debugging. So we still support it, but generally discouraged for supporting that for most. Generally discourage most users from using that for any performance related stuff. But effectively, that's what this when we ask the memory manager to allocate instances explicitly, right? That's effectively the case where we're calling CUDA malloc inside of Legion and bypassing Realm in those cases. So. Just something to be aware of, but mostly you're going to be going down these paths inside Legion. Okay, so let's actually jump back and take a look at that. At what happens if this call returns null? Like we actually are unsuccessful in allocating our instance because Realm said there's no space in this memory, right? Then we need to try to do this. We need to do something to try to make it possible to actually allocate that instance. So if I jump back to well, actually, one more thing I want to do before I leave this method, or before this function. I did promise you that we would take a look at this create layout call very briefly. So let me actually show you that before we jump back. So this create layout call effectively is the thing that actually makes these Realm instance layout generic things. I want to show you where this is. I'm not going to go through the whole method today, but effectively, you can get create layout calls either going through pretty much anything that represents an index space expression, which we haven't talked about, but effectively it represents a Realm index space, whether that's a user visible one like a normal Legion index space, or whether that's one that's been computed like a Legion index space operation that's a union or an intersection of two user visible index spaces, right? They all come to the same place. They get the Realm index space associated with themselves, and then they call this method create layout internal. So you see there's create layout, right, actually, here's the first create layout, index space operations. There's also create layout on index space nodes, which are user visible index spaces. These are index spaces that like Legion clients created, right? They do the same thing. They get their realm index space and they crawl create layout internal. And so if we go look at create layout internal, this is where we actually make this this realm instance layout generic, right? And this is probably one of the more sophisticated methods in Legion. It has a lot of responsibilities to do. Effectively, what it's doing is translating, a realm index space, a set of constraints, a list of fields and stuff, and creating a realm instance layout generic from that, depending on, are we making a compact instance or not making an affine instance? If so, do we have sparsity? And how do we generally translate all those constraints that I showed you early in the program to a realm description of the same thing? The one thing that I will show you just briefly in this method is the main thing the first thing that this method does is it actually tries to create, all the different pieces. So every instance layout generic in Realm can contain multiple pieces, which are like different tiles of your data structure. Now, if you make an affine instance, that will just have one tile, one big tile that represents all the bounds of your instance. But if your index space is sparse, maybe you want to make a compact instance that actually makes, pieces for each of the rectangles in your realm index space, right? Or if you have a tiling constraint in here, right? Maybe you want to tile your index space into multiple different pieces. That all gets handled in this code here. So like, this is actually the dense case here. And it actually, will effectively give you just one piece unless you ask for tiling constraints, and we'll go and compute all the tiles for that to create all the pieces. This is the compact case where you actually have like, you have a sparsity map, right? And you actually want to pull out all the rectangles in that sparsity map and actually, store them in the list of pieces and so forth. So like there's a lot of detail in this method or in this function. It probably needs to be broken down a little bit more. Most of the more interesting stuff is like how you interleave fields with index spaces and stuff like that. And so you can definitely come take a look at this code. This function could probably almost do its own lecture on all the stuff that's going on in here. And so I will probably come back to that. But I do want you to be aware of this create layout call, right? I would treat it mostly as a black box. It converts all these constraints into instance layout generics, and that's the main thing it's doing. But if you do need to go introspect something in here, please let me know if you have questions, because it's a pretty detailed thing. Okay. Let's actually jump back to what happens here in this allocate physical instance call when create physical instance actually fails, right? So we were looking at create physical instance. We looked at how it did all of its stuff, and either it gives us back an instance manager saying it succeeded, or it gives us back a null manager saying, hey, we weren't able to successfully make this physical instance, right? And if that's the case, now we need to try to collect some existing instances to actually be able to make space to try to do this allocation again, right? So if we issue some delete calls to Realm, right, deleting some physical instances, that will hopefully free up enough space that a future create physical instance call could actually succeed and pass back, or actually succeed in doing an allocation. Okay, so let's actually look at this this garbage collector here. So notice that we're going to make a collector which is going to sort of set itself up and get some state about where are the instances that can be collected. And then we're going to repeatedly test whether, have we collected everything that we know about, that we think we could collect? And if so, try to perform a collection and get back an event when it's safe to try again. And, then potentially call back into this instance builder to try to do this collection again, contingent upon this event precondition being satisfied. And by the way, I should probably have pointed out that if you look in collect or in this create physical instance call, right, you're actually getting in, or actually, let's see, where is the create physical instance? Here it is. You're actually getting an event precondition to tell you when to try this allocation again. And that precondition is getting passed in to this this create physical instance call. So Realm knows not to try this allocation again until this precondition has actually been met. Right. So the garbage collector does sort of know when it's done doing enough stuff and tells Legion when to try the allocation again. Okay, so there's pretty much two methods. We're going to look at the constructor for this garbage collector, and then we're going to look at these perform collection and collection complete calls to sort of see what's happening. But you can actually see sort of the logic here. It's just these sort of make the garbage collector, continue doing stuff until it's done, right? And then do enough collection until you think it's safe to try this allocation again. Okay, so let's actually go look at the garbage collector here.
One quick question about what you just said about the precondition. Is that essentially like a lower bound? Because you said that Realm will tell you, here's the point where it's safe to start using this instance. Right.
But the precondition is actually saying when to try the allocation again, right? So you might actually do some work, right, to try to do some like some of this deletion might actually need to be deferred. Like it might involve, like deleting a physical instance may require some communication, right? And so you don't want Realm to try the allocation right away. You want to know that like all the deferred deletions have been issued before it tries to do the allocation again.
Okay, but the precondition is essentially the point where you're asking to do Realm, is there enough memory at that point in time?
Right, exactly. And so you want to make sure all the deferred deletions and stuff that we're about to do here in the garbage collector are issued at that point so that Realm can see them all before we try to do the allocation again.
Got it, thanks.
Makes sense? Yeah, okay. All right, so this garbage collector, what you notice is that it's taking in this list of collectible instances from the memory manager. These collectible instances are all the instances which do not currently have valid data, right? And so effectively they're the things to try. And importantly, notice that we've sorted them by their garbage collection priority. And we've sorted them in not the normal order, right? So we're using standard grader as the comparator here, which means that we want to delete these in the order of highest garbage collection priority first, right? So high garbage collection priority means that they are the first things to try to collect, right? And this garbage collection priority comes from the mapper, right? Every mapper can set a garbage collection priority on every instance. And so the garbage collection priority for any instance is just the max of the garbage collection priority set by any of the mappers, right? So if two different mappers set the same or set different priorities on the instance, right? Whichever one set the higher priority is the priority that will actually be stored in this set here. Right, we're going to use these garbage collection priorities to sort of order the set of order the the way that we try to do collections or collect these physical instances that are eligible for actually doing this collection. Okay, so we pass all this stuff in. We initialize some stuff like we start with the current priority that we're trying to collect now, right? And so the interesting method call here is perform collection, right? This is the thing that's going to try and collect a set of instances enough to the point where you think it's worth trying to do another instance allocation attempt, right? This method is reentrant, right? It can be called many different times as you go around that while loop many times, right? And so what we do is, we're looking at these collectible instances. We look at our current priority, right? So we have a priority that we're trying to collect. We start off with the highest one, but eventually it's going to migrate down to lower and lower priorities until we get to the bottom and say we've tried all of the priorities to collect, right? And so the first time that we get called in here, we look at our current set of collectible instances for the current priority that we're trying to collect. If this is the first time that we've been called for this particular current priority, the first thing we're going to do is look through all of these instances in this particular priority, and we're going to sort them. And the way that we're going to sort them, we're going to sort them into three categories. We're going to sort them into what we call the perfect holes, the small holes, and the large holes, right? So the perfect holes are effectively the instances which are eligible for collection that are exactly the same size as the instance that we're trying to create, right? And the idea is that we want to try to minimize fragmentation. So we want to know, if we can use a perfect hole, that's often better than using, something that's imperfect, right? Because then you're going to minimize fragmentation by collecting something that's exactly the right size. If it's less than the needed size, we put that in the small holes, right? Holes that are smaller than the instance that we're trying to make. If it's bigger, then we put it in the large holes, right? Right, and of course, there's also a filter here for cases where these instances are already deleted by something else, and we can prune those out and not include those in our list of holes and so forth. And then we can set sort current priority false in case we have to in case we return early out of this method and we come back around for the same priority. We know we've already sorted all the instances for this particular priority, so that way. We only sort each priority one time as we're going through it. Okay, so the first thing we try to do, right, is for this particular priority level, try to delete any of the instances that are perfect holes, right, that are exactly the right size shape for for the instance that we're trying to allocate, right? And so we can do the collection on those things. We're actually going to look at this today. It requires more machinery and understanding to actually go look at how this collect call works. But if it succeeds, then we've effectively succeeded in collecting this. We get back an event saying when that collection has succeeded. That's going to be the precondition for trying the next allocation. This collected RT event is going to be the return event, which will say like when it's safe to try the allocation again. And then we can erase this and record that we actually deleted this physical instance. And so if we're able to successfully delete a perfect hole, then we're done, right? Go back around and try to do the allocation again. We just made something that should be like exactly the right shape for Realm to go make another instance to fill in for that new instance that we're trying to make. Right, so we want to go through all the perfect holes first, right? So we might come back, if there's multiple perfect holes, right, we'll try the first one, and return. If that didn't work, then we come back around and we try the next perfect hole, right? We come back into this method from the outer while loop, come back through here, we skip the sort current priority because we already did that, we try the next perfect hole, right, and so forth. And so this method is reentrant and can be called, or not reentrant, but it can be called many different times, sort of repeatedly until we've actually successfully done the allocation or gone through everything. If none of our perfect holes were able to be deleted or there weren't any or whatever, right, next we try the larger holes, right? And we do them in order based on their size, right? So we sort them by their size order with the smallest ones, the ones that are closest to but still bigger than our size, right? These are all the large holes, right? So we try all them in order based on, whatever ones are closest to our size first, gradually ramping up to the biggest ones that are the farthest away from our size, right? Because we're trying to minimize fragmentation, so we try to collect the things that are closest to us first in size. And again, if any of those succeed in collection, we can return right away and try again. Otherwise, we remove them and keep going, right? To the next size, we loop around this thing until we've gone through all the large holes, right? And if we've run out of like large instances to collect, well, now we're down to like the small holes, the holes that are smaller than us, right? And again, effectively what we try to do is we try to sort them into ranges, and we try to group those ranges together into sets that are, we effectively are building sets of instances here that are contiguous in memory, trying to make or find a set of them that actually create a contiguous hole that will be big enough to actually try our allocation, right? And so effectively building this sorted ranges, right, is important for actually trying to do that. And if that doesn't work, we can't actually get anything that's like big enough. Well, then we're like in our last ditch effort where we just go through and start trying to clean up holes that actually are tiny, and for the future, for when we go to collect the next sort of range, right? We want to try to collect all the things in this garbage collection priority order or priority before we go to the next one. I should point out these ranges are actually spanned across the priorities, right? So we track these ranges across priorities such that, if your priorities, if one priority isn't enough to create a range that's big enough, potentially the next priority will actually have an instance that actually aligns with some of our pre-existing ranges such that they actually match up, right, and create a hole that's big enough, right? So we always want to delete like the smallest possible holes, right, even in our priority before we move on to the next one. Right, and if we get all the way down here and we haven't returned anything, or we haven't returned back to try to make an instance, what that means is we've effectively exhausted all the instances in this particular priority. So we're going to go to the next priority, set the sort to true so that we actually do the sorting the first time through, right? And then we can go back around and try again, right? And so the garbage collector will do this exhaustively until it either succeeds in making an instance or fails in not being able to make an instance. I apologize for the vacuuming noise. Yep, and so effectively, the garbage collector just tries to collect everything that it can until it actually either succeeds or it fails and is unable to do so, at which point it will return back to the user to tell it like that it was unable to create that physical instance and actually make it. So that's the garbage collector. And actually I'll show you one more method here, which is if we actually look at the garbage collector and look at where's the test for whether we're actually done or not. Actually, it might be in the header file. Let's see. Yeah, the garbage collection complete is a really simple method here, right? It's just testing whether your priority makes it all the way down to never priority, right? And effectively, if you've made it there, then you've exhausted, all of the priorities in the list of eligible things, and you're actually like out of things to collect, right? And it's actually a pretty simple test, right? So coming back to, let's see, I can search for allocate physical instance. Right, so effectively, if you make it here, you've gone all the way around this while loop until you've tried all your collections, right, and you return here and you're still null, then you're effectively returning that your physical manager, is null, and you've failed your allocation. So anyway, that is instance allocation, and pretty much all the other methods, like if you're just creating a physical instance instead of doing find or create, they all go through the same path of allocating physical instance and stuff like that. They all come through here to try and make the instance, and if not, use the garbage collector to clean things up. So when you guys are wondering, how instance allocation actually works, this is all the stuff that's going on behind the scenes. So with that, I think we're at time for today. So I'm happy to take any questions people might have. But otherwise, next week will be a Realm week, and in 2 weeks, we're actually going to have a visiting lecture on the Legion profiler from Elliot Slaughter from Slack. So for those of you that only come to Legion meetings, 2 weeks will be actually something on the Legion profiler.
So I have a question related to a bug, actually, a recent one related to fields that seemingly are deallocated more than once, or
Okay.
at least that might have been the suspicion. So for debug purposes, is there a possibility to a priori mark fields as never deallocate or something like that, so that they don't get?
Yep. So Legion physical. So this is all about physical instances. So Legion resources like fields and logical regions and partitions and stuff like that, they have their own collection mechanism.
Nice.
And those are actually all going to be reference counted. And what will be necessary to describe all that will be a description of how distributed reference counting works in Legion, which we have not done yet. But you're actually asking for something different, which is you actually want the user to be able to mark that, like, a field or like some Legion logical resource, right, like a field or a partition or something, should never be collected, right, during the rest of the application.
Yeah.
That would be something that we could add pretty trivially. It would require a little bit of plumbing, but certainly we could add such a thing to say, like, raise an error if you ever try to delete this particular Legion resource. But that's a very different path than like the physical instance collection that actually occurs for the mappers. Yep.
And last question from me. About find or create physical instances, it looks like that method lives in 3 versions: the memory manager, the runtime, and
the mapper manager.
Yeah. Mapper.
Yep.
So I was wondering, wouldn't that be a case where some refactoring is needed and bring all this functionality under the same abstraction, maybe the same class?
Well, I actually think it's important to keep them separate. I actually want them.
Okay.
I actually want, like, the runtime and the memory manager and the mapper manager to all be different things. One thing that you could argue, actually, one thing that I was thinking, you might clean up is, I think actually the responsibility for, like, this. So if we look at find or create physical instance, I actually think that, like, this functionality, which determines whether or not we're on the right node or not, right, or on the inner node, right, that could almost be refactored in, like, you could almost consider that should be the runtime's responsibility for making sure, or for testing if we're on the right node or not. The one thing that's a little weird is, like, this find invalid instance call, right, kind of muddies the water there a little bit, because that is a property of this memory manager, right, and so the memory manager wants to do this before it sends the message, right. But otherwise, like, you could imagine, like, this find or create physical instance, this logic to determine whether we're on the owner node or not should actually really be in, like, the runtime call here to check to see if we're on the right node or not. So it's a little muddy, but yeah.
But the different versions have completely disjoint functionality, meaning that
They do.
okay, if you need to do a change in one of them, you don't have to do it
That's
in
right.
the others.
Oh,
Okay.
you mean like the argument calls, or like if you change the parameters, you're going to need to pipe it through everywhere, unfortunately. But
Well,
they're doing.
where I'm coming from is an anti-pattern called Solutions Pro or Shotgun Gallery, where the same method is the same functionality is replicated in many places. And one symptom for that is that if you have to change in one place, you have to change in all the others.
So there's completely different functionality here, right? So like, okay. Because I mean, if you look at like the, what the mapper manager is doing here, right? Like it's effectively managing the, the lifetime of this mapper call, right? And then dispatching to the runtime to go do something different, right? And then the runtime does something different and then dispatches to the memory manager to do like it's part of the process. So it's the same API call, but there are very different functionalities happening, in these different places, right? So.
Thank you.
Yep. Any other questions?
If I try to make a remote instance, how do I know that hasn't been... You said there's a path where you can do everything locally, but don't you need to check that it hasn't been garbage collected on the remote node?
Yeah, that's part of the trick of this. So I didn't show you the collect method. So this let's see. Everywhere that you see this collect method invoked, it's invoked a couple places in this function call. So it's there, it's here, right, on the different hole sizes. Right, like this collect method effectively does something to check to see if it is safe to collect this physical instance. And there is a distributed protocol for checking to see if it is safe to actually perform the collection. And it will deduplicate across races of multiple collections happening in parallel. It will also, like for example, if multiple mappers had called create physical instance in the same memory at the same time, right, they could potentially be executing in parallel on different utility threads or utility processors, right? This collect call actually will deduplicate across those. It will also deal with like checking to make sure that it will also deduplicate against like acquire, or not deduplicate, but manage races against acquire operations being done by mappers on remote nodes. There is a distributed protocol in the mapper manager, in the physical manager for actually doing that. And we don't have time to look at that today. But it will be a topic of a future talk to look at how that protocol manages those races that can occur.
Okay. So the remote node can check its local cache for an answer, but when it's actually time to use it, it needs to acquire it.
And what I will say is that there is a bias in the protocol. There's a bias towards making acquires fast and collects expensive. So effectively, like the way to think of it is that it didn't used to be the case, but this is actually the case now, and it seems to be working much better, is that like when I showed you also the acquire call, right? So like in the, where was it? In the finder create physical instance, not this one, in the memory manager variant, right? Let's see. Actually, it's an allocate physical instance. Sorry. Is that right? Where did the acquire call go? It was actually in like the find satisfying. Right, there's the acquire call here, right, if the user asked us to do the acquire. What I've done, that's also on the physical manager method, or manager class, by the way. So you notice both acquire instance and collect instance are sort of like the competing, where'd it go? That's can collect. So like the acquire and collect are effectively the two things that compete with each other. And there's a bias to make acquires fast and collects expensive, right? And the thinking for that is that acquires should be much more common than collects, right? Collection should be much more sporadic. And so collect actually will be much more expensive. You'll see the protocol will be much more expensive for collect to prove that it is safe to do a collection, whereas acquires will sort of be the default fast case and only slow down if a collection is in progress. And so we'll definitely look at that protocol at some point to see how the physical manager objects that have copies on multiple different nodes, make acquires fast and collects correct. It's kind of the way to think about it.
Right, got it.
But yeah, that's
future class.
It will be a future class because that protocol it's not terribly complicated, but there's definitely a few states to it, and definitely requires some slides to be made. So, yep. Okay. Any more questions for today? All right. So next week is Realm Week, and the week after that will be the Legion Profiler. I'll be taking a little break from giving Legion talk myself, but look for something on the internals of the Legion Profiler in 2 weeks. All right. See you guys next week.